sum of an infinite geometric series. But to get there, we need to talk a little bit about some vocabulary. Remember a list of numbers like this: a sub 1, a sub 2, a sub 3, and a sub 4, and so on. And of course, these terms just represent numbers, is called a sequence. And this would be an infinite sequence. Well, if we take the sum of the terms of a sequence, we would call it a series. So a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus, and continuing, would be called an infinite series. Now, what we're going to be talking about is an infinite geometric series. So let's look at an example. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus, and on it goes. So you could confirm that this is geometric, because if you take any term and divide by the previous term, you would get the same ratio. 1/2 divided by 1 is 1/2. 1/4 divided by 1/2 is 1/2, and similarly for every pair of consecutive terms. But our goal is to find out what the sum of this infinite geometric series is. Now, to do that, let me remind you about our formula for the nth partial sum of a geometric sequence. S sub n was equal to a sub 1 times 1 minus r to the nth divided by 1 minus r. Well, let's use this formula, and I'm going to be very casual in how I write this. You don't generally see this, but I'm just going to think in terms of n being infinity. So just for this time, I'm going to write s sub infinity. I won't write it like that after this problem. But let's consider what this would look like. For this particular problem, the first term is 1, and then we would have 1 minus, our r value is 1/2, so we're raising 1/2 to the, well, infinity power, and we're going to divide by 1 minus 1/2. Now let's consider this, 1/2 to the infinity power. What happens when you raise 1/2 to the infinity power? Well, we can't actually do that, but we could think about it. 1/2 to the first is 1/2, and then when you square 1/2, you get 1/4. You raise it to the third power, you get 1/8. To the fourth power is 1/16, and those numbers are getting smaller and smaller. It was 1/2, and then 1/4, and then 1/8, and then 1/16, and then 1/32. And consider multiplying by 1/2 an infinite number of times, and notice this is getting ever smaller, and it would approach 0. So we're going to say this term goes to 0 in this infinite case. So the sum would equal 1 times 1 divided by 1 minus 1/2. And when we do the when we do the arithmetic there, we have 1 divided by 1/2, which would equal 2. Whoop, you can't quite see that. 1 divided by 1/2, which equals 2. So we would say the sum of this infinite geometric series is equal to 2. Now, the more terms you add, the closer you would be to 2. Even if you added 10,000 terms together, you wouldn't get the value of 2. But we're considering this in the infinite case that the sum would equal 2. And usually we just write s, no infinity there, and we would have the sum equals 2 for this particular infinite geometric series. Let's look at another one. let's let the infinite geometric series be 3 minus 1 plus a third minus a ninth plus a 27th, and so on. And you can't tell that's a third very well. Let's see. You could confirm that this is an infinite geometric series. Notice your R value is negative 1/3. Let's jot that down. R equals negative 1/3. So it's an alternating series. It's going back and forth between negative and positive, negative and positive. So if we use that same formula that we did before, the sum would equal the first term, which is 3, times 1 minus, and again we have this ratio raised to an infinity power, divided by 1 minus negative 1/3. Always take care when you have that negative ratio and you're careful with that subtraction. But just as in our previous case, we have a fraction that is between negative 1 and 1 that's being raised to a larger and larger and larger power. And if you consider what happens when you raise negative 1/3 to powers, it starts at negative 1/3 when you raise it to the first power, but then it becomes positive 1/9 and then negative 1/27 and positive 1/81, and keep raising it to powers, and notice this will also go to 0. So let's write that it goes to 0. So the sum then would be 3 times 1 over 1 minus negative 1/3. And let's simplify. 3 over 1 plus a third is 4/3. So we have 3 times 3/4. I'm just taking the reciprocal of this fraction and multiplying. So we would say the sum of this infinite geometric series is 9/4. Now, let me just point out that if you just added 2 terms or 3 terms or 4 terms together, you wouldn't get 9/4. But let me show you what you would get. If you found the second partial sum, that means you just added 3 and negative 1 together, you would get 2. If you found the third partial sum, you have 3 minus 1 plus a third, you would get 2.333, and the 3's go on forever. 2 1/3. The fourth partial sum I've calculated, and it was 2.22222. Notice this is a little bit smaller than 2 1/4. Remember, this is 2 1/4 here, or 2.25. I'll even write that as a decimal, 2.25. We know that's the value of this sum. Notice this is a smaller than 2.25, bigger than 2.25, smaller than 2.5, but getting ever closer. If you find the fifth partial sum, it is 2.259259, and on it goes. Notice now we're just a little bit bigger than 2.25. The sixth partial sum is 2.246913, and on it goes. The seventh partial sum is 2.251028. And notice the partial sums are getting ever closer to this particular number. And if we found the 100th partial sum, it would be very, very close to this value, although it wouldn't be exactly equal to it. But let's come back and look at where this sum comes from. In each of the previous cases, you'll notice this piece went to 0 right here and right here. So if we eliminate that and look at this particular part of the equation, what it looks like is that we have the first term multiplied by 1 divided by 1 minus r, and that was the same as in the previous case. So the question is, if you have an infinite geometric series, will this be the sum? Because here's what it looks like. Let me write it out formally. It looks like the sum, let me use summation notation. The sum of an infinite geometric series, which we know we could write this way, right? I just have used summation notation. It looks like you could find it by taking the first term and dividing by 1 minus r. That'd be kind of handy to be able to use that formula. So let's look at the next infinite geometric series and see if it seems to be the case. We have 1 plus 2 plus 4 plus 8 plus 16 plus, and so on. You can confirm that r is 2 for this problem. And if we tried to find the sum using this formula, we would start with the first term, which is 1, and we divide by 1 minus 2, and we would get a value of -1. And clearly, this is not the case. This sum would not add to -1. So this formula can't be true in all cases. So let me talk about why it doesn't work in this particular case. Let's go back to this formula. S sub n equals a sub 1 times 1 minus r to the nth divided by 1 minus r, because that's how we got there on the previous two problems. So our sum would equal the first term, which is 1, times 1 minus r, which is 2, to the infinity power divided by 1 minus r. And here's the distinction. Notice in this problem, we're raising 2 to the infinity power. Now 2 to the infinity power, if you start looking at powers of 2, you'd have 2 to the first, then 2 to the second, then 2 to the third, and 2 to the fourth, and so on. So this particular term did not go to 0 as it did in the two previous cases. Let me remind you the two previous cases. Right here, the r value was -1/3, and in this case, our r value was 1/2. And it turns out that your r value must be between -1 and 1 in order for this expression to go to 0. And we had 1/2 in a previous example and -1/3, but 2 does not, raising 2 to a power does not end up with an expression that goes to 0. So this formula is valid only if r is between -1 and 1. And sometimes you see people write it this way: the absolute value of r is less than 1. So we can have an r value of 3/4 or -3/7 and still use this formula, but we can't use the formula if r is anything larger than 2, or greater than or equal to 1, or less than or equal to -1. We say that if a series, excuse me, has an r value between -1 and 1, the series converges. It settles down on a number like it did here. In this case, we say that the sequence diverged, or the series diverged, because it didn't settle down on a particular value. If you look at this, the numbers are getting bigger and bigger and bigger, and this is going to head off to infinity as you start adding the terms. So let's look at a problem and see what kinds of things we should be able to do. The question is, does the series converge or diverge? And then if it converges, can we find the sum? So remember, whether it converges or diverges depends on our r value. confirm that we have an infinite geometric series here. And notice if we take one term and divide by the previous term, you'll find that r equals, I'll just do the division, -5/2 divided by 5. The arithmetic tells you that you would have -1/2. And you can confirm, multiply by -1/2, multiply by -1/2, multiply by -1/2. Now, -1/2 lies between -1 and 1. So that means this series does converge. That means we can find the sum. And the sum would equal the first term divided by 1 minus r. So our first term is 5. We have 1 minus -1/2. So we have 5 divided by 3/2. And we'll take the reciprocal and multiply. We have 5 times 2/3. So the sum is 10/3. So as you keep adding in more and more terms, the sum will get ever closer to 10/3. And we say the sum of this infinite geometric series is 10/3. Let's do another one. The same question, I didn't write the directions down again, but the question is still the same. Does the series converge or diverge? And if it converges, what is that sum? So we're looking at for our R value. To find your R value, you can take, if you know that it's geometric, you can take any term and divide by the previous term. Doesn't matter which ones you use. I will use the first two. So I have 5/4 divided by -5/8, which we know is 5/4 times -8/5. And we find that our R value is -2. Well, that -2 is not between -1 and +1. So this series diverges, and we cannot find the sum for that series. Let's do our next one. Same question. Does the series converge or diverge? And notice I wrote the series with our summation notation. If you find it helpful, you can write the terms of the series out, substitute in k equals 1, and you would get 9 times 2/3 to the 0, which would just be 9. Substitute in 2, and you would have 9 times 2/3 to the first power, and you would have 6. Similarly, you could substitute k equals 3, and you would have 4, and on it goes. But notice on this one, our R value is looking at us right here. R equals 2/3. 2/3 is definitely between -1 and 1. So we can say that this series converges. And because it converges, that means we should be able to find the sum. The sum, remember, is the first term divided by 1 minus R. So my first term is 9. Divide by 1 minus R. So I have 9 divided by 1/3, which we know is equal to 9 times 3, or 27. So as you add these terms, the sum will get ever closer to 27, and we say in this infinite case that the sum equals 27. Let's do one last problem. And this is to express this repeating decimal as a fraction. Remember, this is 0.77777, and the 7s go on forever. So we could write this as 0.7 plus 0.07 plus 0.007 plus 0.0007, and you could continue. It's asking us to write it as a fraction, so let me just move to fractions. This isn't strictly necessary, but I'm going to anyway. We have 7/10 plus 7/100 plus 7/1000 plus 7/10,000, and on the fractions go. So I hope you can see that we have an infinite geometric series here with our R value equaling 1/10. Well, because our R value is between 1 and -1, we can use our formula that says the sum is equal to the first term divided by 1 minus R. So we have 7/10 divided by 9/10. And if we just multiply by 10 over 10 in this problem, we will see that we get an answer of 7/9, which may have been a fact that you already knew, that 0.7 repeating is equal to the fraction 7/9.